All right, I think we'll go ahead and get started. Welcome everybody to week 3 of this seminar series. It's a pleasure to have you here again. I want to first start off with thanks to the Global Institute for Water Security and Jay Familietti for helping to organize this series with a lot of the Global Institute. A lot of the machinery in motion to make this happen with Mark and Michelle and many others. I also want to thank, as always, John Pomeroy and Global Water Futures for underwriting this series and enabling us to reach the other Global Water Futures partners through our simulcast and through our recorded lectures. Don't forget, next week we have Adam Ward coming from University of Indiana. Adam is a specialist on the river corridor, so talk about stream groundwater interactions. It'll be an exciting lecture. But today I'm really happy to introduce our speaker, Witold Krajewski, who I've known for probably 25 years or so. Witold's had a harrowing journey getting here. He came yesterday early via Calgary, but as some of you might know, Calgary had a 30-centimeter snow dump, shut down the airport, and it's lingered into today with massive backlogs. So Witold has kindly agreed to give this from his impromptu hotel room in Calgary, and as he waits for his flight to now go back to Iowa. So Witold, I can't tell you how appreciative we are of your patience with all of this, and apologies for this Canadian weather you're experiencing. I also want to thank our EMAP colleagues who are rolling with the punches and have spent the afternoon really doing heroic work to make all this happen. So to introduce Witold, he is the Rose and Joseph Summers Chair of Water Resource Engineering at University of Iowa. He's also a professor in the Department of Civil and Environmental Engineering at the IIHR Hydroscience and Engineering program. And in 2009, he was appointed to be the director of the Iowa Flood Center. Witold is really, I think, the global leader in radar rainfall. His work focuses on measuring, modeling and forecasting precipitation using various radar approaches and satellite remote sensing approaches. He's published over 250 papers in this area and received many awards quite deservingly. He's a fellow of the AGU, a fellow of the American Meteorological Society. In 2018, he received the AMS Hydrologic Sciences Medal. He was editor of Advances in Water Resources. And in 2012, he was chair of the Kawasi Board of Directors. So Witold is clearly a thought leader and we're in our field, and we're very lucky to have him with us, albeit remotely. And Witold, I'm just going to tell you what a star you are, because here's the crowd that you've assembled, and you're not even here. So I'm just kind of panning the camera around. Here's some over here, and then over here. I'm going to keep you fixed on this part of the audience, just so you have some people to talk to while you're chatting. Actually, I'm going to turn it this way. Oh, there's Saman waving to you. I'll put it this way, guys, on EMAP, because it's shining into the light otherwise. Okay, so with that, I'm going to turn it over to you, Witold, and hopefully all of the high-tech gadgetry works out.
Okay, thank you very much, Jeff. Good afternoon, everybody. Thank you, Jeff, for the introduction, and thank you for the invitation. And at this moment, I should say I'm glad to be here, but I'm not glad to be in the hotel room. I would much rather be with you and to have an opportunity to see the institute and the centers, institutions that the world is talking about. I was also very much looking forward to visiting my friends and to my discussions and chats with Professors McDonnell, Professor Familietti, Professor Pomeroy, Professor Creed, and Professor Razavi. Well, Mother Nature prevented that from happening in person, but I'm glad that I can tell you about our research and the topic. Well, when Jeff proposed this somewhat generic topic of breakthroughs in radar rainfall, I decided to keep it with only a slight modification, so from radar rainfall to radar hydrology, because I believe that broader context is very important. And I decided to keep it because it is more challenging to think in terms of breakthroughs here. So before I proceed, I have to give you some context. And of course, it has to be hydrologic, context. So at first, where is Iowa? Well, the cab driver asked me, this. So here it is, not too far from Chicago, and just, south of you guys. In Iowa, we get floods, many of them. In 2008, this is what happened in the city of Cedar Rapids. That's where the local airport is. And just, look at that. It was a total mess, a big disaster, record flooding. The cost of this disaster just in this one city, about $4 billion. To the economy of Iowa, more like $8 to $10 billion. And also on our campus at the University of Iowa, this is what happened. And the recovery is ending only now, 10 years after. And the total cost of the recovery with rebuilding from scratch some of the functionality, some of the buildings, the total cost reaching $1 billion. So, well, in 2009, the state legislators, they realized that at the University of Iowa, we have some relevant expertise, and through a legislative process, they established the Iowa Flood Center. And not only that, but they also gave us money. But they did charge us. They told us certain things that we should do. Because in 2008, there was a realization that there is lack of information and lack of ability to forecast, floods and to help people, dealing with them. So they put us to work. Well, that didn't happen in vacuum. So the name of the institute that Jeff mentioned in his introduction, IIHR, Hydroscience and Engineering, under a slightly different name, this institute will celebrate 100th anniversary in just 2 years. So this was the backdrop for that legislative action. By the way, in 2008, we were evacuated from this, building for some, 10 weeks. The institute specializes in fluid mechanics, in river hydraulics, river mechanics, hydrology, and everything, fluids. Well, the flood of 2008 was not the only flood. Look at this map. These are presidential disaster declarations over some 60 years in Iowa on a county-by-county basis. So there are 99 counties in Iowa. And if you look at the numbers, so if you add them up, it's over 1,200. So that doesn't sound like what a presidential disaster declaration frequency should be like. After all, these presidents are busy. Yeah, we know about that. In any case, we get floods even now. So as I was leaving, town to come here, we had forecasts of some major floods. So after flash flooding, now many rivers are full, and there is river and flooding, going on. Well, so now, again, in the spirit of providing more background, I will list some of the key developments by the Iowa Flood Center over the last, few years. So in 2016, we finished a 6-year-long project of developing statewide inundation maps. And so from hydrography based on the LIDAR topography, so we are lucky in that sense. We are only one of a handful of states that has statewide coverage by LIDAR data. to hydrology, which is also known as flood frequency estimation, to open channel flow modeling, so setting up models that mimic how water flows in open channels, to mapping the results of those models. So one big, project. In addition, we have developed some 5,000, probably now more, probably close to 8,000 of detailed inundation maps for some of the largest communities, 20 plus and counting. So for these maps, we know not only the out-of-bank topography, but also bathymetry of the river bottoms. And then we use two-dimensional open channel flow models to develop those maps. We provide, these maps to the public through a specially developed interface. We also share these maps with the federal agencies. Another activity, we have developed and deployed what we call bridge sensors, which measure through ultrasonic waves, measure the distance from the bridge deck to the water table. Again, this is in response to this lack of information about what was going on in 2008. So 250 of those you see one here in action during a flood somewhere in Iowa a few years back. So we changed the landscape, the stream monitoring landscape in Iowa. Of course, there are USGS gauges, there, but not that many. Roughly 150 of them. So adding 250, that's an accomplishment. Even though the technology that we use is different from what the USGS does, but when you look at data from a collocated, sensor, so there's an example, then you cannot distinguish. You see actually two lines, but it's hard to tell. So they measure what they are supposed to measure. This is another manifestation of the good engineering that we have done. So just a couple of months ago, there was a big flash flood in Des Moines, the capital of Iowa. And you can, see here how quickly the water was rising, exceeding the flood levels. And then the bridge got submerged. So there was no communication for a period. But then, or at least corrupted communication, corrupted data. When the water went down, then the data transmission resumed. And it happens this way because we test the sensors before we deploy them. So this is the current, map of the USGS stream gauges, the green points, and the blue ones that we deploy and operate. Of course, we share the data with the federal agencies. We also show or get access to USGS data as well in real time. If you look at the histogram between the two as a function of drainage area, you can see that the tendency for the Iowa flood bridge sensors is to cover smaller watersheds. And I will come back to this point later on. Well, the third major activity is statewide real-time stream flow forecasting or flood forecasting when there are floods. So, of course, to do this, we had to develop a hydrologic model, a rainfall runoff model. We could have used some of the many existing, models, but we selected to develop our own. It has the roots in the scaling, theory and scaling, work of our colleagues, Vijay Gupta from University of Colorado in particular, now retired. So this model is based on the concept of landscape decomposition only into two elements. hill slopes and channel links. Hill slopes are not little, squares, but they are what they are, so have irregular shape. What you see here is a very nicely looking river, network. So the blue line is not an image from the satellite. It is a digital representation of the river network that we got from the terrain data. Another view, no coding in colors. They are just to distinguish one hill slope from another. So a hill slope always drains to a link, and then links put together make a river network. Well, so another way of looking at this model is something like this. Rainfall transformation to runoff happens at the hill slopes, and then the water is delivered through different pathways to the channels, and then it is transported through the river network down the stream. So mathematically speaking now, the beauty of our model is that it can be written in the form of ordinary differential equations, so a large system of the ordinary differential equations. So the solution of such a system is much easier than if this was a system of partial differential equations. For the state of Iowa, you can see that this means, roughly 2 million of equations that one has to solve if one wants to make a real-time, forecast. Well, I will not go through the equations. So basically, this is, what I said: transformation of rainfall into runoff components, and then routing of the water downstream. To solve this system fast, we have developed a special, solver. So we worked with our colleagues in applied mathematics at the University of Iowa, and that's why we can solve the system of a couple of million equations within 15 minutes. We update our streamflow forecasts everywhere every 15 minutes or so. And we integrate the equations for about 5 days, ahead. So now, of course, the major input to this model is radar rainfall. So I'm getting only now to the topic of my talk. Iowa is covered by a network of 7 NEXRAD radars. You probably heard, the name. So that's the U.S. network of weather radars operated by the National Weather Service. We get raw data in real time, well, maybe with a 5 to 10 minute, delay, and we make rainfall, maps ourselves. Well, and again, I will elaborate on this in a minute. Now, the fourth activity is to bring all this information and to share it with the public. After all, we were called to serving Iowans, so the fruits of our work have to be available to the people of Iowa. We do other things, research, of course. We educate students, have a extensive graduate, program. So we don't compromise academic, standards, but nevertheless, our customer number one are the people of Iowa. So we developed a browser-based, system. You can just Google it and check what's going on, as we speak. Don't do it now. Through that, system, we make forecasts even for small communities. We have over 1,000 small communities that are located by streams and rivers. So even for those communities where there are no gauges of stream gauges of any sort, and then of course it's difficult to give people the amounts in cubic meters per second because that is totally meaningless. So we developed some indices that we use, and we communicate, those. We also have another way of visualizing these indices as a color-coded river network with time control, so one can see what's going on back in time and forward in time. We can look at rainfall in different, contexts. Clearly, when it comes to flooding and at different scales, then the time integration is something, important. So here you see highlighted in green on the calendar 2 weeks worth of rainfall. Now, this model is calibration free. and I say this a little bit, with a smile. So I've been saying publicly that model calibration kills understanding, and I stand by it. I spent 6 hours with Professor Saman Razavi when we were both in India. We were sitting next to each other on the bus, and I tried to explain my point of view. I tried to convince him. I'm not sure if I succeeded, but I know that he knows what he's doing. So, but this is just a joke. This is just so that I cannot tell him this in person. So. Well, this is what I was taught when I was an undergraduate student or graduate student in Poland. So if you don't like your model, change your model, okay? But things got corrupted a little bit, and now we keep the model, but we just play with parameters. And I just don't think that that's good, because this way you adapt your model into the uncertainties in the input, among other things. But that's the key complaint, by me. So I think that this modeling, or a model component should be analyzed and evaluated on their own. And only if we are happy, then you bring them, together, and then you have a full model. So here I will be talking about the input, but actually in conjunction with the model. But we do look at the input on its own. Have done many studies that Jeff alluded, to in the introduction. So I will just, move on, here. But clearly, calibration free doesn't mean data free, and of course it doesn't mean that you don't look at the data, that you don't look at the model output, and so forth. And we do ad nauseum. Just a quick animation, here of how our model works. A small basin. So because again the structure is river network, based, then you see very quick responses at very small scales, and then a much slower response at a larger, scale. Now, okay, so now that the question is, because, many people talk about different methods of calculating infiltration and runoff, and so we ask ourselves, this question. Okay, so we have a very, we have a simple model, but should we really worry about, this? And so we conducted this numerical experiment. So this is what you see is a graph of what happens in our experiment at a hill slope, So you have a variety of models, here, from simple linear models to more complicated models to a non-physical model that is shown in red, some crazy oscillations, here. So probably it doesn't happen like this, who knows. But what these models have in common is that over time they deliver the same amount of water to the channel, and then that water propagates through the river network. So let's track this water as it propagates through the river network. So here we develop some simple measure. It just took one of them as a reference. It really doesn't matter which one is a reference. And just calculate a mismatch. So when we go to this very small scale, there is a big mismatch between what you see. As we go to the next, scale, well, things moved a little bit, still quite a big difference. And so we go. And now when we are at a large, scale of 10,000, square kilometers, you cannot tell the difference. And of course, you couldn't tell the difference or you couldn't tell where this water, came from. So how is this important for radar rainfall investigations? Well, so there is a full analogy, here, and the analogy goes like this. Suppose that I have a river network and I have radar observations, and at one location, at one hill slope, the true rainfall is the green amount, and my erroneous rainfall is the red amount. And then somewhere else, I made also a random error or an error. So the green amount is the true amount, and the orange is underestimation, severe in this case. But both points happen to be equal travel distance from the outlet of the basin. And of course, at the outlet, you couldn't tell that there was anything, wrong. Right, so that's the benefit of the river network and understanding how water, flows. So river network filters out random errors, and it's actually quite efficient at this. So this is from another simulation study. Again, if the errors are random, and they can be, whether they are correlated or not in space, it doesn't make that much of a difference. That randomness can be significant. So here we look at the effect of resolution. So basically averaging that randomness, and this is what you get. So when you have high resolution, then there is still filtering out of these errors, pretty fast, and at large scale, everything looks great. When you compromise your resolution, then you suffer at small scales, but not that much at the large scale. So 2 kilometers versus 4 kilometers, essentially there is no difference, even starting with a scale of 100 square kilometers. Well, so there is something, there. If you do the same exercise in time, so with temporal resolution, so it's not, that good, because a delay begins, to form. And of course, people typically use data at shorter accumulation than 24 hours. But the National Weather Service, U.S. National Weather Service, they make forecasts every 6 hours for river stream flow predictions. So we are, somewhere in the middle here. Well, okay, so now simulations are very nice, but with simulations you can, get what you want to get, essentially. So it is nice to look at real data. So here in an experimental analysis that we conducted, we are going to use data from USGS stream gauges, not the Iowa flat center stream sensors or bridge sensors. And why? Well, because we don't have as good rating, curves for the locations where we have the bridge sensors, because the bridge sensors don't measure discharge; they only measure the distance to the water table. But of course, hydrologic models, if they use the principle of mass conservation, then of course they give you discharge. So now you have to do something with that if you want to compare it with what a bridge sensor shows you. And of course, for that you need a rating curve. So we have some rating curves estimated using some synthetic modeling-based methods, but they are not as robust as what USGS does by going to every site every 6 weeks or so and measuring both discharge and stage. So this is the network that we are going to use. And one of the scientific, questions, here is, so we all know this inequality, that this is, true. But an interesting, question is, should we provide rainfall data at very high spatial resolution and let the river network do the filtering? Or, on the right, should we do the filtering and aggregate rainfall data and then put all of that into the hill slopes and then the rivers? Well, so we know, again, mathematically that the two are not equal. However, it happens, sometimes that you may get a statistically significant difference that is practically insignificant. So I'm afraid that this is what's going on, here. So if you can see the square grid, so it's in gray, well, then you can also see that for these radars, if you are far away, as on the left, then the averaging is quite different than if you are close to the radar on the right. Well, okay, so this now brings me to the radar rainfall. So in answering these questions of what are the key features that a radar rainfall field should have to ensure as good streamflow forecasting as possible, we decided on the following, strategy. So we have two rainfall products, one that is produced in-house, so I mentioned, this, and the other is produced by National Severe Storms Lab. It is called MRMS. It stands for multi-radar, multi-sensor, because they do use rain gauge data for correcting radar estimates, and occasionally in the West they use satellite data, so that's why multi-sensor. So these two products are similar. Of course, the raw data come from the same network of weather radars, and they do this for the whole country, the U.S., and we do it only for Iowa. You can see by just quickly looking at these images, so different columns are for different, resolutions, but the same, product. You can see that they are similar, but that they are different. And so because the algorithms that they use and the algorithms that we use are somewhat, different. Again, the generic steps are the same, but details are different. Which one is better? Well, that is hard to answer. I will show you more on that later on. We do certain things, differently. For example, in Iowa, we have many wind farms. And I would claim that we do the cleaning of the wind farm echo a little bit, better than they do. But they use rain gauge correction, which we don't. So we have a pure radar-based product. Our maps have higher temporal resolution, so we have a new map every 5 minutes. Our maps have half a kilometer resolution. They are 1 kilometer, 1 hour. They do have a higher temporal resolution product. However, they have to wait for an hour to make a correction with rain gauges, and that's why the hourly product. Well, different, grids. So for MRMS, it is easy because the spatial resolution is 1 kilometer, so you can easily do upscaling. For us, it's we start with a lat-long, grid, so different projections. So there are some differences, there. But the details here for us today do not, matter. Now, we are going to look at these products, but through the eyes of our hydrologic, model. And so the model will be the same for both, products. And the key statistic that we will be using to evaluate the model performance is this Kling-Gupta efficiency index, one of many measures known in hydrology. This Nash-Sutcliffe is not something I'm crazy about. This one I like more because the interpretation is much more straightforward. So basically, variance ratio, bias ratio, and correlation. Well, okay, so the first results on the topic of this, seminar, is this a breakthrough or not? Well, so what you see performance at these, let's call it, 150 gauges. Of course, the evaluation to get the KGE index, you have to have some period of time. So for us, it's 1 year. So you are that way divorced from individual events. So this is the performance for the same model for different resolutions. So you can see that when you get to this larger scales, 1,000 square kilometers and up, there is hardly any difference between the three. And the three, 1 kilometer versus 8 by 8 kilometers. Now, when you go to smaller scales, well, there are some, differences, there. The same holds for our product. So the units in the upper left corner, that's in grid units. So, but the message is the same. Higher scales, larger scales, no difference. When we go to time, now, well, here you see some differences. Again, the range is quite a bit, from 1 hour to 24 hours. So especially at smaller, scales where things, happen, quickly, then you see significant, differences. And the same for our, model as well. If I now do resolution to resolution comparison like this, well, they are almost, identical as expected. This is for our model. This is for MRMS. MRMS seems to be a little bit tighter, and if I toggle between the two, then I have to give the slight victory to MRMS because they moved up to higher values of the performance index. So according to this index, they do slightly better. If I do the same in time, again, we have bigger differences, MRMS and IFC, maybe a little bit less, but still differences. And if I compare for the same resolution the two products, well, then we see that they give quite different, results, right? So now if you count the dots below and above, there are more dots below. So again, victory may be by decision to MRMS. But quite a few, quite big differences in the performance. Exactly the same hydrologic, model. So one conclusion could be that rainfall is important. So we all knew about, this, but nevertheless, this is a controlled, confirmation. Now, if you look at the map of Iowa and the same, index, well, this is only for our, model. So we don't do that bad. However, we do have a problem in western Iowa. And so I will not, dwell on this. We know we have a problem in western Iowa. It's exactly, the same, model. There are some differences in the input, but I don't think that they are significant enough to warrant such a big and poor performance, or big difference in performance and poor performance in western Iowa. Now, let's take a more hydrologic view at what's going on. So maybe some of you heard that with radars, there's this range effect. Well, it's pretty clear as the beam goes higher and higher in the atmosphere. At some point, maybe it's shooting above the clouds. So how can it see rainfall? Before it gets there, often it has to go through the melting layer, so below which there is rainfall and above which there is ice. So that gives rise to a very strong but artificially strong signal. So if you don't recognize this, then you can be fooled, and you may think that there is a strong rainfall, there. So range effect is something well known to radar hydrologists, but corrections are not, that easy. So here let's look at this range effect, but in the context of width function. So everybody knows what a basin or river network width function is, but roughly it is the distribution in terms of distance or in terms of travel time, if the velocity happens to be constant, from any point or over the basin to the outlet. So here you see the units of travel time for Cedar River with the outlet in Cedar Rapids. So that was that city in my first, photo. So now if you say, okay, so nominally these radars in the U.S., they have a range of 230 kilometers. But some people say that only up to 100 or maybe 150 the data are or could be good. Above that, not so good. Well, so this is, if we limit the range of these radars to 150 kilometers, so we see 3 radars looking over this basin, well, then a big portion of the basin will not be covered. And if we look at this in terms of the width function now expressed not as a travel time but as a distance, so the outlet is on my left. So you see that the major contributions to the outlet, to the stream flow at the outlet, are from the distance range of 200 to 300 kilometers along the river network. So for one radar, this would be the coverage. For another radar, this would be the coverage. For the third radar, this would be the coverage. If you put them, together, this is the coverage. So it looks like there should be, something, there. So if we look at the hydrologic model performance through the eyes of this width function, that perhaps we should see something. So we took a look at this and many other things. So here it is in terms of the radar range, but from the outlet to the from the radar to the centroid of the width function, and it's a mess. I don't see any clear, pattern. There is no pattern with respect to whether a basin is large or small. The same for the other, product. Different arrangement of points, but still no clear pattern. If instead of going to the centroid, we go to the peak of the width function, so that's where the most water is coming, from. Well, again, quite messy, picture, develops. So we continue looking at it, this way, but it's just not that easy so far. No major breakthroughs. Well, so then we did another, exercise. So here we said, okay, so since we already learned from all these, simulations that what really matters is the total volume. So not that much the distribution in time or space, but the total volume over a basin, over an event. And because MRMS had a slight, advantage in the competition so far, and because it is gauge corrected, then we said, okay, we will equalize our product in the sense of mean areal rainfall hour by hour to MRMS. And then let's see what happens. So you see what happens. So before we did that, the blue is our original product. After we did that, then essentially all the blue moved to become, red. And so the two products became much closer. Again, when I say this, it is through the eyes of the same hydrologic, model. Now, okay, so that may be, interesting. However, there is, little help in that of how, like for us at the Iowa Flat Center, how should we correct our, product? Well, we can correct it with rain gauges. One reason we don't do this is because the network is pretty sparse, there, and we know the data quality is not, that high. They do it anyway because they do everything that they do for the whole country, so they don't look back, they don't apologize, they just do it. So anyway, but to better understand of what really matters, we need to continue this investigation, because to say that, okay, so the means are the same, but other descriptions of the products are not the same. So we want to figure out what is that they differ with that matters for the performance of the hydrologic, model. So that's what we are after. We are building different tools to help us with this. I will not walk you, through this, but tools that would allow user to ask all sorts of, questions vis-a-vis the locations of the sensors, the respective drainage areas, the width function, the location of the wind farms, etc., etc. So that work is in progress. And now, just to finish with the spirit of radar rainfall, there is a third product on the way. Whether it will help or not, it's hard to tell. Both NSSL and Iowa Flat Center, we are working on another methodology for radar rainfall estimation based on the signal attenuation. Right now, the methods use reflectivity, which is which is highly nonlinear, and therefore these algorithms are highly sensitive to the observed reflectivity. With attenuation is nearly linear or linearly related to rainfall. So there is some hope that maybe better estimates are on the way. There are some limitations of that method, in particular that effect that I mentioned, that radar beam is looking higher and higher into the atmosphere. You cannot overcome this one, and it may be the dominant one, but it's hard to tell. A little bit more of a comparison. So we do use rain gauges. We do look at them, but we don't have them in the operational real-time stream of forecasting. Well, what is particularly attractive, here, so if you look on the right-hand side, so we have this rainfall estimation using attenuation with a range correction. And if we look then at the data, you can see that there is, some improvement. So again, now that may help us, or it may further confuse us with respect to answering, these key questions. What is it that really matters? Well, so that takes me to the national, scale. You guys could ask, this, what was so profound that you said today? Actually, a couple of, things. First of all, the system that we operate is, as far as I know, the first large-scale, fully automated stream flow forecasting, system. The U.S. National Weather Service has a human with human neural networks heavily in the loop. I have to admit I'm ignorant of the procedure in Canada, but I don't know of any other country in the world where there is a fully automated prediction. Now, of course, that has some dangers, which we see from time to time. But that's the challenge. That's the future. So now the U.S. National Weather Service is attempting to do very same, but for the whole country. So I believe Jeff is going to visit in Alabama, soon enough. So probably they will talk about this. So they are trying to do what we have done in Iowa. So we know that computationally, of course, it can be done, but there are major challenges along the way. And before I finish, let me just say about a little, kind of a going joke between me and a colleague, Ricardo Mantilla, a former student of Vijay Gupta at Colorado and a key developer for the model that I was, talking about. So when something goes wrong, so then Vitek, that's so I say, hey, Ricardo, your model is not so good. And Ricardo says, hey, Vitek, give me good rainfall, and you'll see what the model can do. So with this, I want to thank you. Thank you very much. Again, my regrets that I couldn't, make it, and maybe another time will be a lucky day. Thank you.
Well, thank you very much, Vitek. That was really a terrific presentation, especially under the circumstances, so thank you. I'm not sure, Terry, how we're set up for questions. It's going to work okay. We've got time for some questions, and we have the technology. Please use the microphone. Maybe Saman, just grab it if you can. And I'm going to pass the this camera monitor, try to train it on the questioner here. Here's your busmate from India talking, Saman.
Yeah. Hi, Vitek. Yeah, sorry to miss you here. Thanks very much for reminding me of the nice memories in India and on that bus, on that bumpy road for 5 hours. And thanks very much for trying to convince me that calibration kills understanding. And I've quoted you on that. And you made it, so you convinced me. But probably halfway, probably we need to take another trip and go on that bus for another 5 hours or so, and then I will be fully convinced.
Or the other way around, yeah.
Yeah. So, very nice presentation. 2 questions. The first one, and what we are really struggling with here in hydrologic modeling, in particular large scale, at the scale of a province, is water management, regulation of flows, control structures. And I wonder how you handled that, or what's the magnitude of that problem in the state of Iowa, and how you could get around that, or could you bring the operation in somehow? So that's one question. And the other quick question is that, so you showed you had a mixture of different parameterization schemes for the storage and release function on that screen. So some linear reservoir, some nonlinear. And that included a sinusoidal function. I wonder if you have seen evidence somewhere that the relationship between storage and release of a hill slope, for example, or a catchment at any scale could look like that. Yeah. Thanks. So I pass it.
Yeah. So thank you, Saman, and again, my regrets that I was not able to visit, with you in person. Well, to answer your first question, so the regulation of the flow is not a big problem in Iowa. We have 4 reservoirs, large, well, not so large for Iowa. Again, the landscape doesn't support large storages. that are operated by the U.S. Corps of Engineers, and they are nice enough so that they share the projected releases with us. And then we include them as the initial conditions to integrate the stream flow below those storages. So that's an easy one. We also have included in our model, but not the operational model, but there are a few basins in Iowa where there are many farm ponds. Now, the farm ponds, they don't have what I call active control. They have passive control. But nevertheless, there is an effect on the stream flow. So we have that capability in the model. We have done online, simulations, actually even, published, a couple of papers on that. But we don't have this in the operational model. And one reason is that when these farmers have these farm ponds, of course, they keep them full because they want to enjoy, a little body of water and go fishing or swimming. And so when those are full, then their effect, on discharge is not that significant. For your second question, no, we don't see any evidence of that. The idea here was to do something that is clearly not physical, and then to show that even if you do something like that at large scale, it will not matter. As long as you put the right amount of water into the drainage network.
Yeah. Good. Thank you, Vitek. Next question, John Pomeroy.
Hello. Thank you for your seminar. We really enjoyed it. Your photograph at the end is eerily reminiscent of Saskatchewan, and that's the basis of my question. And also, as you raise farm ponds, one of the issues we have in Western Canada is a tremendous impact of depressional storage on the contributing area for runoff generation. And I'm wondering if you have these types of important issues in Iowa, and if you do, then how do you handle it in your hydrological models? Because we find it very challenging.
Yes, we do find those very challenging as well. So probably, so many of you know that Iowa has been significantly engineered in terms of drainage. And this is particularly true in western Iowa and in the very flat places, there in the floodplains of the Missouri, River. And there are rivers, there were channels that people built that if you just look at the topographic data, you just don't see them. So we think that our bad performance in western Iowa is partially caused by that our representation of how water flows on the surface is just wrong. And so we have some evidence of that, and we have plans to correct it. Now, we also have more and more tiling in Iowa. And so even in places where there is relief, there's not flat like in the picture, but where there is maybe, 30-meter elevation, difference, so there's enough flow for the water to flow, they still put tiles. And so because tiling increases yields. So right now, we are not really dealing with that. So we get good performance maybe by luck, and maybe where we have poor performance, maybe it's because of that. We know that we are not handling the recession part of the hydrograph very well. So from the flooding point of view, maybe it's not that important, but from the hydrologist pride, of course, it is very important. And so, and we also have the Des Moines lobe where we have many depressions, and we don't have any special way of dealing with that, although we are looking at different ways of modeling connectivity that would change as the state of the water in the basin, changes. And so, but those developments are yet to come.
Any other questions? One quick question from me, Vitek, as I pass the microphone, if you can hear me. I guess as I didn't hear any mention of groundwater, and I'd probably bet a week's pay that most of the water forming the flood hydrograph in many of those basins is groundwater, not rainfall, if you thought of it compositionally using some tracers of some sort. And I'm just wondering if you ever have conversations on that topic with your team of model developers and the thinking of about the model structure, and perhaps others on the team who might be possibly echoing those kinds of comments. Has that come into any of the discussions thus far?
Yeah. No, of course we have discussed this. Unfortunately, in Iowa, we have very few research wells. We do know about our geology and the deeper aquifers, and we also know about the alluvial, storages, but they are not very well monitored.
Yeah.
So that's well, just to give you a kind of an embarrassing, example. That for a while USGS operated in the state of Iowa 9 automated wells. Then a couple of years ago they reduced this to 1 because of the budget cuts. Well, the Iowa Flood Center, with some help with some other funding, we recently installed 20 that are being monitored automatically, and so with data reported in real time.
Right.
So as we learn more, I'm sure we will seriously consider including a groundwater component.
Yep. John, one last quick question.
Yeah, quick question.
Yeah.
I'm wondering if the inundation maps that you produced had any effect on the cities and counties where there was property shown to be inundated, or that could be, that wasn't previously known.
Well, with so many floods in Iowa over the last 60 years, this would be difficult for something like this to escape, if I understood your question correctly. But one set of these maps, the statewide maps, they are in the FEMA lingo. So FEMA is Federal Emergency Management Agency in the U.S., and they have certain standards, and according to that lingo, those are approximate maps, but they have regulatory power. Now the more detailed maps, we hear very good things about them as floods occur. Some emergency responders, they flew drones over flooded areas and they compare them with our maps. So because the major difference there is that the statewide, they are linked to discharge probabilistically. So of course the biggest uncertainty is right there in hydrology, in flood frequency. On the other hand, the more detailed ones, they are linked to observations from a USGS gauge. So we have a map every 6 inches, or so.
Good.
And so they are just much better calibrated.
Okay. Well, Vitek, on behalf of the group here, and we have a terrific crowd. I hope you've seen some of them as I'm panning here. They've come for this virtual lecture. I want to thank you for a really clear and lucid talk. It's very compelling. Many of the issues you're dealing with in Iowa, I think, are issues we're dealing with here. So we thank you for that. We're with you in spirit in Calgary, and we hope you get home safe tomorrow. And for those that are here, before we clap and thank Vitek, just know that there's tea and coffee and cookies, courtesy of Michelle and Mark and others, and we'd like you to stay and chat out in the vestibule as we continue the discussion. So thanks again, Vitek.
Thank you, everybody. Thank you all.